Okay, so let's continue to look at the next one. Negative 7n over 2 minus 3n here. So for this series, the easiest one actually is using the nth term test. Okay, so all we need to do is to show that you see this limit as n goes to infinity, negative 7n over 2 minus negative 3n. It actually equals negative 7 over negative 3, which is 7 over 3. And we know that this limit does not equal 0. So based on the nth term test, this series actually is diverges. Okay, so that's problem D. So let's take a look at the other problem. Let's see problem E here. Okay, problem E here. So for this problem here, we can have a couple of examples. So the first example, what we can do is we can use the integral test. Okay. So basically set fx equals ln x to the power of 100 over x. Okay. And then x is greater or equal than 2. Actually, it's not that bad to figure out that the derivative and to show that this is positive continuous, right? And then not increasing. Okay, so the three conditions. Well, to show that it's not increasing, all you need to do is to take the derivative and set it equals 0. It's pretty easy to evaluate that based on the quotient rule and the chain rule. So it satisfies those three conditions. So basically the problem becomes 2 to infinity ln x 100 over x dx. Okay. So to evaluate this integral. Well, to evaluate this integral, what we know is, we can make a substitution, but it turns out that this problem, it is not that challenging. So from 2 to b, right, this is an improper integral. Ln x 100, right, times d ln of x, right? Because the derivative of ln x actually is 1 over x. So with that, this what we can do here is, so the antiderivative of this one, it turns out it's going to be ln x to the power of 1 over 1 actually is over 1 over 1. Okay, so you can actually evaluate it. So take the derivative of this, so it's 1 over 1, 1 over 1 cancel out, give you ln x to the power 100, and then times the derivative of ln x is 1 over x, so it's bingo back to here. Okay, so it's good. And then you can see that literally, if you plug b inside and let b go to infinity, this integral will become infinity. So hence, this series actually diverges. Okay, diverges. So that's one way to do that. The other way to think about this is you can make a limit comparison. So for here, you can do is limit comparison test. So let the comparing test series is 1 over n here. Okay, the harmonic series. And, so if you take the limit as n goes to infinity, so take the ratio of this. Okay, take the ratio of this. And then, so you're going to have ln n to the power of 100, okay? And this actually going to goes to let's see, if you take this limit, so that actually goes to infinity. So I think that using the limit comparison test in this way actually does not work. Okay, I take my words back. So because we're trying to use the limit comparison test, one thing we need to do is that we need to make sure that the limit actually equals a positive constant. So, that's the first thing. I take my words back, guys. Actually, it works because the limit comparison test said that if the ratio of those two functions, of those two expressions equals infinity, and the denominator series actually is diverging, then the idea is you can still get that the original series, it diverges. Okay?